hello all. Hannes Reinecke speaking. Most of you might know me. I'm actually, well, now it works. I was wondering. I'm a storage architect nowadays and doing, well, storage things and block layer and everything in this direction. So, recently I had a look at NVMe-TCP and NVMe-TCP performance. I have bored you already with NVMe topics in the recent years, so I decided to skip the NVMe introduction, what this is, why this is, and why you should be using it or not. And in a similar vein, I'm not doing an introduction into NVMe-TCP because that is, surprise, surprise, NVMe over TCP. Who would have guessed? So, think of it, if you have no clue, think of it about better parallel iSCSI, because that's really what it is. So you can do everything and fast over the network. Well, you should be able to do everything and fast over the network. Turns out that this wasn't really or really is not the case because, well, a partner of ours did run some tests and got some curious results. Like, all right, you know what? We tested this one and put a bit of scalability behind it and some performance, and then suddenly the thing slowed down, or rather, run into a timeout. And then the controller would reset and the performance was down the drain. That is not good. So, but I said, yeah, right. I mean, could happen. Let's have a look. But then I digged around and digged around and digged around. This entry was a Buxilla entry from May 2024, meaning last year. And, well, I had a look, but really no good progress. I had a presentation at ALPS in autumn last year, asking them, Reinecke, has someone an idea? Has anyone seen something like this? And I got the response, yeah, you know what? The link is oversubscribed, user error, forget about it. Well, tell this our customer, thank you. Not that helpful. So, continuing with digging, continuing with stuff. Right. So, what happened was that this customer was creating 72 namespaces, i.e. devices, and mapped them to the host, and then running I/O across all of them. Which is, yeah, okay, apparently this was too much for this link to the storage array, and we got timeouts. Okay, because the I/O got slowed down because the link only had a definite finite bandwidth. So yes, okay, yes, we can understand. But then these are 72 namespaces. That is hell. Scalability is something else. I mean, on SCSI, we tested easily tens of thousands of devices on SCSI on the same from the same storage array, and really never had any problems, even with iSCSI. So what's on earth going on? Why? Why do we see it here? Well, so the thing is, this is the block layer. This is block layer multi-queue, where you not only have a device, but each device has several queues. And to be efficient, you map these queues to CPUs, or rather a set of CPUs if you're not having enough queues. So, for example, CPU 1 till 4 would be mapped to QA, and 5 till 8 would be mapped to QB. Okay, easy. So, and but then this is TCP, so that would actually scheduling a work queue for handling I/O. As it so happens, you can't really run the work queue on a set of CPUs because, well, you have to pick one CPU to actually run the work queue on. All right, so pick the first one. So the work queue is running on, for QA is running on CPU 1, and the work queue from QB is running on CPU 5. Okay, it's not really optimal, but yeah, that's the way it is. I mean, we can't do it anything else. Okay, fine. So, yeah, but this is for one namespace. We have 72 of them. So the next namespace will be redoing all these assignments and will figure out, all right, and I'm running on CPU 1. And the QB will be running on CPU 5. Okay. Meaning for all 72 namespaces. So all 72 namespaces are running one queue on CPU 1 and the other queue on CPU 5. While the other CPUs are doing nothing. that was not quite what we thought we should be doing. And if you then throw in TLS, which has to do some heavy computation for each I/O, all on the same CPU, yeah, okay, yeah, could run into timers there. Yeah, all right, good, fine. So eventually, we came up with a patch saying, all right, so spread it out across all available CPUs in that CPU set, and that will solve it. Well, no, it did not. That was surprising, to say the least. And then I said, all right, so good, by all means, let's have a look at block trace. So I did. And then I figured, well, I am actually not sure whether it solved anything, because I couldn't actually measure it. And this is one of the typical block trace output which I got. And as you can see, the submission latency here is brilliant. 6 microseconds. Yes, that's cool. But the completion, average, that's microseconds, that is 15 milliseconds. And we are going up until half a second. Yes. Okay. Yeah, and what's more, deviation is all over the place. So deviation, if some of you actually know about statistics, hello, Jack. Standard deviation is in the same range than the average value. That's crap. So basically, forget it. You can't tell anything from that. You can measure it, but you have no idea what you measure because it's completely garbage. That is curious. What on earth? So, okay, let's have a look at the block trace things. What is it we are seeing here? If I find now my pointer again, there we are. So, no, and yeah, there we are. So, and this is the block trace output. And these are the number of queues which we have. So you see, these are microseconds again. So yeah, okay. There's a bit of deviation there. Yeah, okay. So measurement was right. So let's see, does it work? So let's turn it. And then you see, oha, that is curious. So we are actually quite good most of the time. So if we were to exclude this bit, and these bits, we will actually work quite good because as you can see here, this is about what? 250 microseconds? Yeah, it's about okay. So, and what's even more interesting, these are regularly scaled in logarithmic intervals with a power of 2. Something is going on here. But unfortunately, I have no idea what. So I think it might be something to do with the network, and I'm actually pretty sure that has something to do with the network. But really, what? That would be, apparently we have some networking people here. Maybe they know what's going on, but so yeah. Let's get back to the original ones, namely this one here. So, yeah, that was a bit unfortunate. But then I said, all right, good, okay, so this might be, maybe it's the network card. That was only 10 gig rig, so I said, okay, maybe it's the network cards which couldn't handle it any better, and maybe it's some queuing within the cards, what do I know? And I do have some machines with 100 gig in Ethernet, so right, move to a 100 gig array, and then everything will be nice. So I moved to a 100 gig array, or rather, dig through Ortos, found a machine and another machine and connected them up and booted the whole thing up and whoosh, machine crashed. With a really cool error, the BMC said he didn't have power. Which I found, what? It's okay if you don't have power, but how come you can tell me that you have no power? Right. I just said, maybe we should do another machine, maybe. So, yeah. Eventually we figured, well, maybe we overloaded the power rail for the PCI devices because we actually put 400 gig PCI devices on that machine. So it might well be that this might be too much power for the PCI rail, maybe. So it was terribly weird. So I switched the machine, just put in one card, and that's good. And that card even said, "Oh, I'm using 30 watts. So and you have enough power." I said, "Oh, good, thank you." Right. Okay. So I switched to another machine, which I did, and then I got 150 megabytes on 100 gig Ethernet. Really? Oh, that was, as someone said, underwhelming. And so what do we do now? So, okay, but then I figured, right, maybe so, I actually just changed to a different target device. The initiated device system was the same, so have a look there. And then I said, yeah, it could be that we are actually running in excessive scheduling because that's, it's a 100 gig link. It has quite a few of queues and we have quite a few of CPUs. And the whole thing relies on CPUs and IO being aligned. And if it's not aligned, yeah, right, you're constantly scheduling back and forth. So yeah, that might do something. Right, okay. So, and because the thing is that this was one of the areas where we always skirted over from the NVMe-TCP side. So basically, we are just sending things and the network layer will know what we want to do, surely. Okay, right. Because we are aligning everything from the block layer side, everything is nicely aligned, and then send it off to the NVMe side, to the network side, it'll be okay. Yeah, sure? Are you really, really sure? So, as I said, so for on the target side, it's similar as what we do on the host side. So we have incoming IO, which is scheduled on a work queue, and then we're doing this bit, doing send and receive to actually handling the entire packet, and that is fine. So we are running on a CPU, a work queue on a specific CPU. That CPU we can pick off from the incoming packet. It'll tell us, right, I have been received on that CPU. Then we said, okay, so use that CPU, that'll be fine. But that means that all packets, all incoming packets will be handled from the same CPU. Are we sure? Are we really sure that this is the case? And then I had a look in all these grubby details. What can you do with network cards and what have you to do with a network card? So, thing is that is actually a tricky thing because the network card has to do some, well, it has to do some alignment. The network card internally has some queues where to put on the packets. But at some point it has to decide, right, on which queue do I put this packet? And that is okay, but we have a different use case. I mean, our layout might be different from whatever the network card decides to do. So we have to somehow align these things. And there is something called network scaling, network stack scaling. There even is a document, I put it there, which tells you what you need to do. And then it turns out that is freakingly complicated. Oh, well, you know what? There's a hash function which decides on which queue it'll end up. And the hash function is roughly calculated like this. And then you can put it via ETH tools into the driver. So, really? What is that for a daft interface? But then it turns out there's an easier one that is called RFS, Receive Flow Steering. And that actually has a surface interface where I said, oh, that's cool, let's have a look. So RFS is basically you map the queues to CPUs. Well, yeah, that's what I want because, yeah, I have this queue, should be ending up on that CPU. And especially with the higher speed network cards, you will be having enough queues, so you could assign a one-to-one mapping. Each queue should be mapping to a single CPU. So, and that's really what this is. There's an interface called RPS CPUs, which is the CPU mask for this queue. We said, oh yeah, that's cool. So we can send. And then there's a flow count, which is essentially the number of flows on that queue. Whatever this one does, you just set it to a high number and that'll be good enough. So I really have no idea. And then there's the other side, that's the transmit packet steering, which goes exactly which works exactly like this. You either set a CPU mask, or more interesting, you can also set a queue mask. So you could actually have a one-to-one mapping between TX and RX queues, which is really what you want to have, because the work queue is doing send and receive in the same CPU context. So clearly you want to have both on the same CPU. So we are right. Okay, so we can set this. Yeah, that looks good. And and then the incoming packets are being marked with a so-called NAPI ID. This is essentially, well, this is the flow abstraction which the network layer has. So it does a hash over the IP address, source IP address, source port, a target, a destination IP address, and destination port. Does a hash over that one, and that is a flow, essentially. And this flow can be identified with this NAPI ID. I said, yeah, cool, that's what we want. So let's have a look whether the mapping is correct. So I put in some debug print, said, all right, print out the NAPI ID just to see it whether we're correct. I did, and the results was nothing. No NAPI ID. Huh. Again, not really what I expected. All right, so, but maybe you can set it. So I tried to look at the NAPI ID, whatever we have, and try to basically hack it in that I'll set the NAPI ID to whatever Sisyphus said. All right, I did that. Hacked the driver to actually do things. So set the NAPI ID, run the driver, and voila, the print actually came alive and said, yeah, you know what? The NAPI ID, which you said was wrong, but you should use that NAPI ID. Oh, cool. Use that NAPI ID then. So it turns out, whenever you see any valid NAPI ID, you get the correct NAPI ID back. Okay. That is a curious interface. Not sure whether that's correct or whether I did something wrong or something, but that was unexpected again. But okay, it works for me. At least I now got the NAP ID, and now I can indeed figure out, yes, it is nicely aligned. Everything's aligned as we thought. So, and then you can have scripts for setting up the CPU masks. And well, there's the SMT thing, where you have to assign two masks, but 2 bits in the mask. But yeah, that's fine. And maps and everything. And then you can map it, and everything will be good. Only it did fuck all, as usual. So nice that you have everything aligned, but yeah, it doesn't really help. Again, so I said, right, there's perf. Let's have a look at perf, what perf says. And I had a look at perf. Maybe if I get the mouse back. So I think I have to exit here now. So, oh God, oh, I have to find them. Oh, my God. Dum, 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 dum. Hmm. There's my mouse. So, and this is the perf graph from the target side. And there you actually see, yeah, these are the handler queues, the work queues for the individual queues. Yeah, nicely aligned. Yeah, everything's nice, but you just one for receiving. Not really what we wanted. And it's taking up quite a bit of time. Not good. And if we look on the, no, I have another, where's the other one? Dum, dum, dum. And if we align it, this is now after I aligned everything. So it looks slightly different here. So we're not spending that much time, but there's still, so here's the MLX5, that's the reception thread. Just one, why there's one, I have no idea. And then there's the TCP reception, again, running off a different thread, and then everything is handled over there with the K-workers IO threads. So yeah, we did align, but still not quite what we wanted to do. And then I also checked. Sorry? Oh no. Yeah, nearly. Okay. So. So, and this is the flame graph for the initiator side. So, ooh, that doesn't look good. So, oh, come on. That is always the thing. So, yeah, that's the one. So, this doesn't look that good. So, yeah, we're having all these send threads here. Everything's nice, everything's good, but ooh, that doesn't look good. There is a stall somewhere. Something is happening. And this is essentially the same thing what we've seen on the block trace setup, that there is a massive stall somewhere when we're trying to send I/O. And this is even confirmed with in the output. Where are you? Can we see it here? Okay. So, and this even is confirmed in the output of the dmask. I put in some debug run trying to figure out what's going on. And it turns out that we are running into retries when doing a send message. But this is, again, in regular intervals. So for a time period, everything runs nicely. And then suddenly we are hitting retries. Send message returns E again. And we have to retry on several queues. Which queues that is different, but always so. And that is literally thousands of retries, which we're getting there. And then everything continues to run again until, again, we hit retries. So there must be some buffering involved. At some point, we are overwhelming a buffer, but I really don't know which one. So if anyone has any ideas, what I need to do there to tweak things to get it more aligned, that we are basically knowing which buffer we are running against, and also the buffer side, that we somehow can tweak I/O to not overwhelming the buffer, that would be incredibly helpful. And that basically is also the conclusion of that talk. So if anyone has ideas which buffer that is, I'd be so glad.
I do have a question.
I do, yes.
Did you limit the amount of I/O you are trying to do? So is that,
No.
or are you just full blown?
Yeah, sure. I mean, I want to do performance test. Why should I limit it?
Yeah, so I would suggest that you try to limit it and see if there's any point where it works nicely and where it is the cutoff, basically.
That I could try.
At least try.
Well, yeah. So
does it work to some extent?
Well, not really, because the problem is that the driver design is interesting. As you might have seen in the block trace output there, the submission latency is basically nil. And that is because the driver, on submission, it just do enqueue the command, start the command, return. That's all what it does. So it has literally no idea how long it'll take for that command to complete, whether there is any contention, anything. No, it'll be good. I just queue it and return. That'll be good enough. So it makes it incredibly hard trying to limit the incoming I/O, because you don't have any interaction where you could limit things.
Well, you are sending something, so you can just send 100 megabytes per second and not more.
Yeah, I could try to do this via block trace and trying to limit that way. Yes, I could try. Yeah, but then I would know, right? So this is now the best spot. Helping me what again?
You know the magic buffer.
Yeah.
And depending on the answer to that, you might have theories what that buffer is. Yeah, I could possibly.
It gets you more, maybe useless data.
Yeah, oh, that for sure. Yeah, I surely will be getting more useless data, yes.
Maybe it's useful.
Or maybe even, yeah, you never know until you try. Yes, indeed.
Just a basic question. What if the NIC ran out of descriptors? So do you know you don't have any drops on the network card itself? The counters are clear?
No, I think the counters are okay last time I checked, yes.
So there are no drops. Okay.
No, and not with 100 megs. Come on. I mean, this is
That's also probably a basic question, but did you check whether the TCP window closes? Also on the underlying flows? Because this would be the typical.
I do expect that it does, but how can I influence it? What can I do about it? Because closing the TCP window means, oh, right, I'm sending too much data. Yeah, I've gathered as much.
Increase the received buffer size to
so
have a larger window?
Yeah, but in the end, I still would overflow it, right? So I would need to tune the I/O with the buffer size somehow, wouldn't I?
So I'm a user space guy, because I have the window for back pressure, because I don't want to send so much faster than the receiver can process the data.
Yes,
so
that is correct. So
ideally, basically, my consumer consumes as fast as the sender produces.
Yeah, but if it doesn't, I'll end up in this situation. Yeah, you're correct. Yeah, so I would need to. All right, I will have to look there to fiddling with that, hopefully. All right. If there are no more questions, oh, you got another one? Oh,
I'm just wondering, is it possible to configure the NVMe, the CPU that NVMe chooses through the user space SFS or something, or is it like all determined in kernel?
It is actually determined in kernel, and also it's pretty much static in the end. So once it's set up, and it'll be running on that CPU. So it would be different if we would always schedule on a different CPU, but that's not the case. We will always be on the same CPU. So even if we have some crashing, it will always be from the same CPU to the same CPU. So again, hand waving here should be okay-ish. And that really doesn't seem to explain it, because then I would have a constant noise. If I were constantly rescheduling on other CPUs, it would be a constant noise, and that's not what I'm seeing. I'm seeing rather some buffer overflow behavior here. Okay, thank you very much, and enjoy the rest of the content.